Before the war reached its breaking point, engineers were already building machines that looked like they belonged to another century. Jet aircraft without propellers, tanks too massive to move, weapons guided by early automation, ideas that promised to reshape the battlefield forever. Some were real, some never left the drawing board, and others remain surrounded by mystery even today. These are not just weapons, but glimpses of a future imagined in the middle of chaos, where innovation raced against time and reality struggled to keep up. Messerschmitt Me 262, the jet fighter ahead of its time. Speed was the one advantage Germany desperately needed by 1944, and the Messerschmitt Me 262 promised exactly that. Conceived under aircraft designer Willy Messerschmitt and tested throughout the early war years, the project slowly transformed from an experimental curiosity into a machine that looked decades ahead of its rivals. The first successful jet-powered flight on July 18, 1942, proved that piston-engine fighters were nearing their technological limits. Powered by twin Junkers Jumo 004 turbojets, the aircraft introduced a level of acceleration and climb performance that stunned even experienced Luftwaffe pilots. When the Me 262 finally entered operational service during 1944, the strategic situation had already shifted against Germany. Allied bombers escorted by fighters such as the North American P-51 Mustang and Supermarine Spitfire dominated European skies. Against these opponents, the jet's top speed of around 870 kilometers per hour gave German pilots a rare advantage. Units like Jagdgeschwader 7 learned to make high-speed attack passes using 430mm Mk108 cannons to strike heavy bomber formations with devastating efficiency before climbing away beyond interception range. Yet, the aircraft's revolutionary design came with fragile realities. Early turbojet engines were temperamental and required delicate throttle control, often lasting fewer than 25 flight hours before needing replacement. Fuel shortages between 1944 to 1945 limited sorties, and inexperienced pilots struggled to adapt to jet handling characteristics that differed dramatically from earlier fighters. Political interference also reshaped the program. Adolf Hitler's insistence on converting some aircraft into fighter bombers delayed interceptor production at a critical moment when Germany needed defensive capability more than experimental versatility. Despite more than 1,000 airframes being completed before May 1945, only a fraction saw sustained combat. Allied bombing disrupted airfields, spare parts became scarce, and maintenance crews fought a losing battle against mechanical wear. Still, the Me 262 changed aviation history. After the war, captured examples were flown by American and Soviet test pilots, influencing aircraft such as the F-86 Sabre and MiG-15. Rather than a decisive weapon, the jet became a preview of the post-war era, a machine that proved the future belonged to turbine engines, even if it arrived too late to alter the course of World War II. Panzer VIII Maus, the super-heavy tank Germany built. Few armored vehicles captured the obsession with sheer size quite like the Panzer VIII Maus. Approved in 1942 after discussions between Adolf Hitler and engineer Ferdinand Porsche, the project aimed to produce a tank so heavily armored that enemy guns would struggle to penetrate it. At nearly 188 tons, the Maus pushed engineering beyond conventional battlefield logic, reflecting a late-war belief that overwhelming protection could compensate for Germany's worsening strategic position. Instead of prioritizing mobility, designers focused on survivability and raw firepower. The enormous turret, built by Krupp, carried a 128mm KWK-44 main cannon paired with a secondary 75mm gun for additional versatility. Armor thickness reached up to 240mm at the front, theoretically allowing the tank to withstand direct hits from many Allied weapons. On paper, the Maus seemed unstoppable. Reality proved far more complicated once testing began at Kummersdorf in 1944. Engineers quickly discovered that moving such a massive vehicle placed extreme stress on its drivetrain, and overheating became a constant concern during trials. Logistics presented an even bigger challenge. Many European bridges could not support the vehicle's weight, forcing planners to consider unconventional methods like driving underwater using a snorkel system while another mouse supplied electrical power from the riverbank. Even transportation to testing areas required specialized rail equipment and extensive preparation. These problems highlighted a growing disconnect between engineering ambition and battlefield practicality. By early 1945, Germany faced severe fuel shortages and relentless Allied bombing, leaving little capacity for experimental heavy armor programs. Only 2 prototypes were completed, and neither entered combat. As Soviet forces advanced, the remaining vehicles were captured, and components from both were later assembled into a single example now displayed at the Kubinka Tank Museum. The mouse stands as a symbol of how wartime engineering sometimes chased extremes rather than adaptability. While its armor and firepower were impressive, the tank demonstrated that size alone could not guarantee effectiveness. In a conflict increasingly defined by speed, air superiority, and logistical efficiency, the massive vehicle became less a weapon of war and more a reminder that technological ambition must still answer to the realities of the battlefield. V-2 rocked the first long-range guided missile weapon. Long before the space race captured global attention, the foundations of modern rocketry were being shaped under far darker circumstances. At the Peenemünde Army Research Center, engineer Werner von Braun and a team of scientists spent the 1930s turning theoretical rocket concepts into working machines. Their breakthrough came on October 3, 1942, when a liquid-fueled rocket successfully reached the upper atmosphere and returned to Earth under controlled flight, an achievement that blurred the line between weapon development and early space exploration. What made the V-2 revolutionary was not just its range, but its speed and trajectory. Fueled by liquid oxygen and alcohol, the missile accelerated beyond the speed of sound, climbing into the edge of space before descending in a steep ballistic arc. Unlike traditional bombers or artillery, there was no warning once it launched. Interception was nearly impossible with the technology available at the time. Beginning in September 1944, Germany deployed the rockets against cities including London and Antwerp, using them less for precise military impact and more for psychological shock. Civilians often heard nothing until the explosion itself. Behind the technological achievement lay a darker reality. Production shifted to the underground Mittelwerk facility after Allied bombing threatened Peenemünde. There, forced laborers endured brutal conditions, and thousands died assembling the weapons. Each rocket required complex manufacturing processes and scarce resources, placing enormous strain on Germany's collapsing wartime economy between 1944 to 1945. Even as launches continued, the program struggled to produce enough missiles to influence battlefield outcomes. From a strategic standpoint, the V-2 failed to change the course of the war. Its accuracy was limited, and the cost of each launch far exceeded the damage inflicted. Yet the rocket's long-term impact reached far beyond its original purpose. After Germany's surrender in May 1945, American and Soviet forces captured engineers, documents, and hardware, using them to accelerate their own missile programs. The V-2 became both a technological milestone and a moral paradox, a machine that opened the path toward spaceflight, while reminding history that innovation can emerge from some of the most destructive chapters of human conflict. Horten Ho 229, the stealth flying wing prototype. At a glance, the Horten Ho 229 looked less like a conventional aircraft and more like a glimpse of aviation's distant future. Designed by brothers Walter and Reimar Horten, the flying wing concept abandoned the traditional fuselage and tail in favor of a smooth, blended shape intended to reduce drag and improve performance. By early 1944, the Ho 229 V1 completed its first glide tests, demonstrating that a tailless jet aircraft could remain stable in controlled flight, something many engineers previously doubted. The Luftwaffe's interest in the design centered on efficiency and speed. Powered by twin Junkers Jumo 004 turbojet engines in the V-2 prototype, The aircraft promised high velocity and long operational range compared with conventional fighters. Its layout aligned with the ambitious 3x1000 requirement, which demanded a machine capable of carrying 1,000 kilograms of bombs at 1,000 kilometers per hour over a distance of 1,000 kilometers. Engineers also experimented with wood composites and charcoal-infused adhesives to conserve strategic metals, unintentionally creating a structure that some later researchers suggested might reduce radar reflections, though true stealth technology did not yet exist. Flight testing revealed both the strengths and risks of the radical design. Without a vertical tail, control depended heavily on precise pilot input and aerodynamic balance. In February 1945, test pilot Erwin Ziller attempted a powered flight of the V-2 prototype, but an engine failure caused loss of stability, leading to a fatal crash. The accident highlighted how experimental the aircraft remained, especially at a time when Germany faced severe shortages of experienced pilots and fuel between 1944 to 1945. As Allied forces advanced into German territory, development facilities were abandoned or captured, halting further progress. American troops discovered a partially completed Ho 229 at the Gothaer Wagenfabrik plant, where it was later shipped to the United States for evaluation. Although the aircraft never reached operational status, its influence extended far beyond the war. The flying wing philosophy would resurface decades later in designs such as the Northrop B-2 Spirit, proving that the H-0229 represented more than a wartime experiment. It was an early exploration of aerodynamic ideas that would shape stealth and high-efficiency aircraft long after the conflict ended. Tiger II King, Tiger tank, built for extreme firepower. Power and intimidation defined the arrival of the Tiger II when it appeared on European battlefields in 1944. Developed primarily by Henschel, the heavy tank represented Germany's attempt to combine the sloped armor philosophy of the Panther with the devastating firepower of the earlier Tiger I. At its core sat the long-barreled 88mm KWK 43 L71 cannon, a weapon capable of knocking out enemy armor at ranges where many Allied crews could barely respond. During the Normandy fighting in July 1944, Allied troops quickly realized that engaging a well-positioned Königsteiger head-on was often a losing proposition. Protection was its greatest strength and also its greatest weakness. With frontal armor reaching roughly 150 millimeters, the tank could shrug off many anti-tank rounds, giving crews confidence during defensive engagements. Yet, the nearly 70-ton weight pushed mechanical components beyond their intended limits. Engines overheated, transmissions wore down quickly, and maintenance crews struggled to keep vehicles operational, especially during long marches across rough terrain between 1944 to 1945. Fuel shortages compounded the problem, turning even functioning tanks into stationary strongpoints when supplies ran dry. Combat reports from the Eastern Front showed how experienced German crews used the Tiger II to dominate open ground, ambushing advancing Soviet armor from long distances. In defensive roles, its heavy armor and powerful optics allowed precise firing positions that could stall enemy advances temporarily. However, mobility remained a constant concern. Bridges often required reinforcement, railway transport demanded careful planning, and Allied air superiority made movement during daylight increasingly dangerous. Despite its fearsome reputation, fewer than 500 units were completed before Germany's surrender in May 1945. Many were abandoned not because they were destroyed, but because mechanical failure or lack of fuel left crews with no alternative. The tank symbolized an era when engineering sought battlefield dominance through size and firepower rather than flexibility. Today, surviving Tiger II tanks displayed in museums illustrate both sides of that philosophy. They represent extraordinary technical ambition and craftsmanship, yet also reveal how complex machinery can struggle when logistics, resources, and strategic reality fail to keep pace with design goals. Schwerer Gustav, the massive railway supergun project. Imagine a weapon so large that it required its own railway network just to move into position. That was the reality behind Schwerer Gustav, an artillery project developed by Krupp after Adolf Hitler demanded a gun capable of smashing through the fortified defenses of the Maginot Line during the late 1930s. Engineers responded with a machine that defied conventional military logic, a railway-mounted cannon weighing over 1,300 tons, supported by an enormous crew and a logistical operation closer to a moving construction site than a traditional weapons platform. The scale alone was staggering. Its barrel stretched more than 30 meters, launching shells that weighed up to 7 tons across distances exceeding 40 kilometers. Although the original target was French fortifications, the gun's most notable deployment came during the siege of Sevastopol in 1942. Transported across specially reinforced rail lines into Crimea, the weapon required thousands of personnel, cranes, and weeks of assembly before firing a single shot. Reports from the siege described massive explosions that destroyed ammunition depots and heavily reinforced bunkers, creating a psychological impact as powerful as its physical destruction. Yet, behind the spectacle lay serious practical limitations. Every relocation demanded extensive preparation, making the gun vulnerable to air reconnaissance and attack. Unlike mobile artillery that could quickly shift positions, Schwerer Gustav functioned almost like a stationary fortress. By 1943, as Allied air power intensified and Germany's strategic situation deteriorated, military planners began questioning whether such enormous engineering projects justified their cost. The resources needed to maintain and protect the supergun often outweighed its battlefield value. As Germany retreated across Europe between 1944 to 1945, mobility and rapid response became far more important than overwhelming size. Reports suggest that German forces ultimately destroyed the gun to prevent its capture by advancing Allied armies. Today, Schwerer Gustav is remembered less for the damage it inflicted and more for what it represented. An era when engineering ambition pushed the limits of scale without always solving the realities of modern warfare. It remains one of the clearest examples of how technological spectacle can overshadow practicality when military strategy and industrial capability fall out of balance. Heinkel He 162 Volksjäger Emergency Jet Fighter Plan. Speed was no longer a luxury for Germany by late 1944. It had become a last gamble. As Allied bombing raids intensified and experienced Luftwaffe pilots were lost faster than they could be replaced, the German Air Ministry issued an urgent directive in September 1944 for a jet fighter that could be built quickly, cheaply, and in large numbers. Heinkel's answer was the He 162 Volksjäger, or People's Fighter, a compact aircraft designed to rely on non-strategic materials and simplified manufacturing methods that could survive the collapse of traditional factories. Unlike earlier jets such as the Me-262, the He 162 emphasized speed of production over durability. A single BMW 003 turbojet engine sat above the fuselage, reducing complexity but creating unique stability challenges. The first prototype flew on December 6, 1944, an astonishingly short timeline that reflected the desperation of Germany's situation between 1944 to 1945. Wood became a major structural component due to aluminum shortages, yet rushed construction led to bonding issues and structural weaknesses discovered during testing flights. On paper, the aircraft offered impressive performance. Capable of speeds exceeding 800 kilometers per hour, it could theoretically intercept Allied bombers with ease. Units such as Jagdgeschwader 1 began receiving the fighter during early 1945, and plans called for young or minimally trained pilots, even members of the Hitler Youth, to operate the jet under the Volksjäger concept. In reality, the aircraft's sensitive controls and rapid acceleration made it unforgiving for inexperienced aviators. Several training accidents occurred before meaningful combat deployment could begin. Fuel shortages, damaged infrastructure, and Allied air superiority limited operational use. Only a small number of combat sorties were flown before Germany surrendered in May 1945. The He 162 ultimately became a symbol of technological ambition, shaped by urgency rather than refinement. Engineers had managed to create one of the fastest fighters of its era, yet the surrounding conditions made sustained deployment nearly impossible. Today, the Volksjäger represents a stark example of how advanced technology can emerge during crisis. It showed that jet aviation could be simplified for rapid production, but it also revealed the risks of compressing development cycles when resources, training, and time were already running out. Dornier Do 335 File, the fastest piston-engine fighter. Instead of following the familiar twin-engine layout with propellers on each wing, engineer Claudius Dornier pursued a radical solution that immediately set the Do 335 apart from every other fighter in the sky. The aircraft's push-pull configuration placed one engine at the nose and another at the rear of the fuselage, aligned along the center line. This unusual design reduced aerodynamic drag and eliminated the dangerous yaw that occurred when one wing-mounted engine failed. When the prototype took flight in October 1943, it quickly proved that piston-powered aircraft had not yet reached their performance ceiling. Speed became the file's defining trait. Early testing revealed that it could exceed 750 kilometers per hour, faster than most propeller-driven fighters operating during the war. The streamlined fuselage, tricycle landing gear, and carefully balanced weight distribution gave it a sleek, almost futuristic appearance. Unlike many heavy fighters of the era, the Do 335 maintained impressive stability at high speeds while carrying substantial firepower. A 30mm Mk103 cannon mounted through the propeller hub, supported by additional nose-mounted weapons, allowed it to function as both an interceptor and a fighter bomber. Safety innovations also distinguished the aircraft from its contemporaries. Engineers incorporated an ejection seat, rare for the time, along with explosive bolts designed to jettison the rear propeller in emergencies, reducing the risk to pilots during escape attempts. These features reflected Dornier's focus on combining performance with survivability, a balance not always achieved in late-war German aviation projects. Despite its technical promise, production struggled as Germany's situation worsened between 1944 to 1945. Allied bombing campaigns disrupted manufacturing, and resources shifted toward jet programs such as the Me-262. Only a limited number of Do 335s were completed before American forces captured examples at Oberpfaffenhofen near the war's end. U.S. test pilots later flew the aircraft and reported exceptional speed and smooth handling, confirming that the concept held real potential. The FIII ultimately became a bridge between eras, a machine that pushed piston engine technology to its limits while hinting at the performance expectations of the coming jet age. Though it never saw large-scale combat, its innovative layout remains one of the most creative aerodynamic solutions attempted during World War II. U-boat Type XXI, the Electroboot submarine revolution. By the time Allied anti-submarine warfare tightened its grip on the Atlantic, German naval planners had reached a blunt conclusion. Traditional U-boats were becoming obsolete. Earlier designs spent most of their time on the surface, diving only to attack or evade. Radar, sonar, escort carriers, and long-range patrol aircraft turned that operating pattern into a liability. The Type 21 emerged from this crisis as a radical rethink, not an upgrade. It was designed from the keel up to live underwater, not merely survive there. Everything about the Electroboot reflected this shift in philosophy. Its hull was smoothly contoured to reduce drag below the surface, sacrificing surface handling in exchange for submerged performance. Inside, engineers installed enormous battery banks that dwarfed those of earlier U-boats, feeding powerful electric motors optimized for sustained underwater travel. For the first time, a submarine could outrun many surface escorts while submerged, reaching speeds close to 17 knots below the waves, a figure that shocked Allied intelligence once it became known. The Type 21 also redefined offensive capability. 6 forward torpedo tubes were paired with an advanced hydraulic reload system, allowing rapid follow-up attacks without the long rearming delays common in earlier boats. In theory, a single Electroboot could fire multiple salvos in quick succession while remaining submerged, then slip away before escorts could react. Snorkel technology further extended endurance, enabling diesel engines to recharge batteries at periscope depth rather than forcing risky surface runs. The program's execution never matched its ambition. To speed production, Germany relied on modular construction spread across multiple shipyards. Between 1944 to 1945, this strategy unraveled as Allied bombing disrupted transport and quality control collapsed. Hull sections often arrived misaligned, wiring systems failed, and poorly sealed welds caused leaks. Many submarines required extensive dockyard repairs before they were even seaworthy. As a result, the Type 21 arrived too late and too unreliable to affect the war. Only a few conducted limited patrols before Germany surrendered in May 1945. Its real influence emerged afterward, when Allied engineers studied captured boats. Those lessons reshaped post-war submarine design worldwide, changing underwater warfare for decades to come. Landkreuzer P-Tuchstoß Ratte, the unrealistic giant tank. Imagine a vehicle so massive it blurred the line between tank and battleship. The Landkreuzer P-1000 Ratte was conceived during 1942, at a time when German military planners were searching for technological miracles to reverse mounting losses. Engineer Edward Grotte proposed an armored behemoth that would dominate the battlefield through intimidation alone, a moving fortress built not for maneuver warfare, but for overwhelming presence. Weighing roughly 1,000 tons, the concept dwarfed every armored vehicle ever constructed, reflecting a late-war mindset that equated scale with superiority. Design sketches revealed a machine closer to a naval platform than a traditional tank. Twin 280mm naval guns were planned as the primary armament, supported by heavy anti-aircraft defenses intended to shield it from enemy aircraft. Powering such a structure presented enormous engineering challenges. Some proposals suggested multiple diesel engines normally used in submarines, yet even optimistic projections predicted painfully slow movement. Fuel consumption, crew requirements, and maintenance demands would have been extreme, turning every deployment into a logistical operation larger than many conventional armored units. Strategic reality quickly exposed the project's flaws. By 1943, Allied air superiority made slow, oversized vehicles dangerously vulnerable. Europe's bridges and rail networks could not support the Ratte's weight, meaning it would struggle to reach the front lines at all. Military planners began questioning whether resources spent on one colossal machine might be better used on hundreds of conventional tanks or aircraft. Albert Speer ultimately halted development, recognizing that industrial capacity was already stretched thin by existing programs. Although it never left the drawing board, the Ratte remains one of the most discussed what-if weapons of the era. Its legacy lies less in engineering achievement and more in what it represents, a period when desperation encouraged increasingly extravagant ideas. Rather than a practical weapon, the Landkreuzer P-1000 stands as a reminder that technological ambition without strategic realism can produce concepts that capture imagination while offering little value on an actual battlefield. Focke-Wulf Ta, A183 Huckebeen Advanced Jet Concept. By late 1944, German aircraft designers were no longer chasing incremental upgrades. They were chasing survival. Among the boldest proposals to emerge from this atmosphere was the Focke-Wulf Ta 183 Huckebeen, a jet interceptor envisioned as a radical leap beyond existing fighters. Led by engineer Kurt Tank, the project focused on raw speed and climb performance, aiming to intercept high-altitude bomber streams before they reached German cities. Unlike earlier aircraft shaped by wartime compromise, the Ta-183 looked forward, almost detached from the reality of a collapsing front. Its configuration broke from traditional layouts. Swept wings angled sharply backward hinted at aerodynamic theories that would only become standard years later. A single Heinkel HS-011 turbojet engine sat within a compact fuselage, while a high-mounted tailplane promised improved stability at transonic speeds. Designers expected the aircraft to exceed 950 kilometers per hour, a remarkable figure for its era, and heavy armament of 30mm cannons suggested devastating firepower against large bomber formations. On paper, the TA-183 represented a shift toward jet designs optimized not just for speed, but for high-altitude interception efficiency. Yet, ambition collided with timing. Germany's industrial network was already under constant bombardment, and resources were rapidly redirected toward immediate defense rather than experimental prototypes. Wind tunnel tests and detailed blueprints progressed, but no complete airframe ever reached flight status. By early 1945, advancing Allied forces captured design facilities, effectively freezing the project before it could transition from theory to reality. What makes the TA-183 fascinating is not what it accomplished, but what it suggested. After the war, engineers from both the United States and the Soviet Union examined captured research, recognizing ideas that would soon appear in early Cold War jets. Swept-wing aerodynamics, compact fuselage design, and emphasis on high-speed interception echoed through post-war aviation development. The Huckabee therefore occupies a strange place in history, an aircraft that never flew, yet influenced conversations about the future of jet combat. It stands as a reminder that even during the final, desperate months of the war, designers continued to imagine machines shaped more by tomorrow's physics than by the harsh limits of the present. V-1 flying bomb. Early cruise missile of the war. Long before modern cruise missiles became symbols of precision warfare, the V-1 flying bomb introduced a different kind of terror. One powered by automation rather than a human pilot. Tested at Peenemünde and deployed beginning in June 1944, the weapon arrived at a moment when Germany sought new ways to strike distant targets, despite losing air superiority. Shaped like a small aircraft with stubby wings and a pulse jet mounted above the fuselage, the V-1 blurred the line between airplane and missile. What civilians noticed first was the sound. The pulse jet produced a harsh, rhythmic buzzing that echoed across the sky as the weapon crossed the English Channel toward cities like London. At roughly 8 meters long and carrying a warhead of about 850 kilograms, the V-1 relied on a relatively simple guidance system. Gyroscopes stabilized the course while a mechanical counter determined when the engine would cut off. That sudden silence often signaled the most dangerous moment, as the bomb tipped forward into a steep descent. From a technical perspective, the V-1 was remarkably efficient for wartime production. It required fewer strategic materials than advanced aircraft and could be launched from ramps hidden along coastlines or carried beneath modified bombers. Between 1944 to 1945, thousands were fired, forcing Britain to develop layered defenses that included radar tracking, anti-aircraft artillery, and fighter interception. Pilots discovered unusual tactics, sometimes nudging the bomb's wingtip to disrupt its gyroscope rather than shooting it directly over populated areas. Despite its simplicity, the weapon revealed the limits of early automation. Many V-1s fell short of their targets or veered off course, and once Allied forces captured launch sites across Western Europe, the campaign quickly lost momentum. Yet, its broader significance extended beyond immediate battlefield results. Engineers studying captured examples recognized a concept that would evolve decades later: an unmanned aircraft programmed to fly a fixed path toward a distant objective. The V-1 therefore stands as more than a wartime curiosity. It marked a turning point where mechanical guidance replaced human pilots, demonstrating how technology could extend reach without extending risk to aircrews, while also raising enduring questions about warfare conducted at a distance, guided not by sight, but by machinery alone. Panther Ausf G-10. Like Germany's advanced medium armor. When German forces first encountered the Soviet T-34, it forced a complete rethink of armored warfare. The Panther series emerged from that shock, and by early 1944, the AOSF-G variant represented the most refined attempt to correct earlier flaws while preserving battlefield dominance. Produced by manufacturers such as MAN and Daimler-Benz, the AOSF-G wasn't just another upgrade. It was an effort to turn a complicated machine into something capable of surviving the brutal realities of the Eastern Front. Visually, the Panther Ausf-G looked purposeful rather than massive. Its sharply angled armor plates weren't simply aesthetic. They deflected incoming rounds and increased protection without pushing weight into the extreme category occupied by heavy tanks. Combined with the long-barreled 75mm KWK-42L70 cannon, the vehicle could engage enemy armor at distances where many opponents struggled to respond effectively. Crews often described it as a sniper among tanks, fast enough to reposition, accurate enough to strike first. Yet, beneath that reputation lay constant mechanical tension. The Panther's transmission and final drive systems operated near their limits, particularly during extended movements across mud, snow, or broken infrastructure. Maintenance crews worked tirelessly to keep vehicles operational, often improvising repairs with limited spare parts as Allied air power disrupted supply lines. Between 1944 to 1945, logistical pressure became as dangerous to Panthers as enemy shells, with fuel shortages forcing units to abandon otherwise functional machines. On the battlefield, the AOSFG performed best in defensive engagements, where long sight lines favored its gun and optics. In regions such as Poland and East Prussia, German crews used terrain to create layered ambush positions, leveraging the tank's firepower while minimizing exposure. However, strategic conditions continued to deteriorate, and even technically advanced vehicles could not compensate for dwindling manpower and industrial capacity. In the war's final months, Panthers fought from the Ardennes to Berlin, showcasing precision but also crippling complexity. Surviving Ausf FG tanks remind historians that advanced engineering alone never guarantees victory without reliable logistics, sustainable production, and realistic strategic conditions. Blohm Voss BV 141, asymmetric recon aircraft. At first glance, the BV 141 looked like a design mistake, an airplane built without visual balance, its cockpit pushed far off to one side like an afterthought. Yet, this strange configuration was intentional. Engineer Richard Vogt believed that removing the cockpit from the main fuselage would give reconnaissance crews an uninterrupted panoramic view, something traditional layouts struggled to achieve. When the prototype lifted off in 1938, observers expected instability. Instead, the aircraft surprised skeptics by flying with remarkable smoothness, proving that symmetry was not a strict requirement for aerodynamic stability. Pilots who tested the BV-141 described a machine that felt unconventional but predictable. Careful weight distribution allowed the aircraft to remain level despite its uneven appearance, while the glass gondola gave observers exceptional visibility for photography and artillery spotting. In theory, this made it ideal for battlefield intelligence roles. Early evaluations by the Luftwaffe compared it with more conventional designs, and although the asymmetric layout drew attention, performance alone did not guarantee adoption. The project's fate was shaped less by aerodynamics and more by wartime priorities. The BMW 801 engine intended for the BV-141 became essential for fighters such as the Focke-Wulf FW-190, leaving little room for experimental platforms. Production planners favored aircraft that could be manufactured quickly and in large numbers, and the unusual structure of the BV-141 complicated mass assembly. By the time testing matured, Germany's aviation industry had shifted focus toward designs that demanded fewer resources and offered immediate battlefield utility. Even without entering widespread service, the BV-141 challenged assumptions that had guided aircraft design for decades. It demonstrated that unconventional thinking could produce functional solutions, even if circumstances prevented full deployment. Today, historians often point to the aircraft as an example of how innovation sometimes arrives ahead of necessity, a bold concept that proved technically sound but strategically out of place. Its legacy lives on not through combat records, but through the reminder that engineering progress often begins with ideas that look impossible at first glance. Arado Ar 234. Blitz, the first operational jet bomber. By the time the Arado Ar 234 appeared over Europe's skies, air combat had already shifted into a desperate race between innovation and survival. Conceived in 1941 as a reconnaissance platform that could outrun interception entirely, the aircraft abandoned many traditional bomber ideas. Instead of heavy defensive guns or thick armor, engineers focused on raw velocity. When the prototype achieved jet-powered flight in July 1943 using Twin Junkers Jumo 004 engines, it introduced a new philosophy: survival through speed rather than protection. Early missions proved how disruptive that idea could be. Flying higher and faster than most Allied fighters, the AR-234 gathered reconnaissance photographs with minimal resistance. Pilots described the aircraft as sleek but demanding, especially during landing, where the high approach speed left little margin for error. As the war intensified, the Luftwaffe adapted the platform into a light bomber. Bomb racks were mounted beneath the fuselage, turning what began as a scouting aircraft into a precision strike machine capable of rapid hit-and-run attacks. Combat operations during 1944 revealed both brilliance and compromise. Units such as Kampfgeschwader 76 used the Blitz in fast bombing runs during the Ardennes offensive, exploiting its ability to cross hostile airspace quickly. Yet, the aircraft's advantages came with trade-offs. Limited defensive armament meant pilots relied heavily on speed, and long takeoff runs made operations vulnerable to damaged airfields and fuel shortages. Even advanced features like an early autopilot system could not compensate for Germany's collapsing logistics network, which restricted production numbers and operational readiness. The AR-234's real legacy unfolded after 1945. Captured aircraft were examined closely by Allied engineers who recognized that jet propulsion had permanently changed bomber design. Instead of slow, heavily defended formations, the future pointed towards smaller, faster strike aircraft capable of independent missions. In that sense, the Blitz was less a decisive weapon and more a glimpse of what post-war aviation would become. Kugelpanzer, mysterious one-man armored sphere tank. Kugelpanzer, the armored sphere that nobody fully understands. Few wartime machines look as strange or as unexplained as the Kugelpanzer. Unlike conventional tanks built around firepower and armor, this vehicle resembled a rolling metal capsule, more experimental prototype than battlefield weapon. Believed to have been developed around 1944, the design replaced tracks with two large steel wheels and enclosed the operator inside a narrow spherical hull. No confirmed design brief survives, which has left historians reconstructing its story from fragments, photographs, and the single surviving example. What makes the Kugelpanzer especially puzzling is how little protection it offered compared with other armored vehicles of the period. Its thin plating suggests that it was never intended to trade blows with enemy tanks. Instead, some researchers propose that it may have served as a reconnaissance platform or observation vehicle, possibly designed to move quietly along defensive lines while minimizing its visual profile. The narrow viewing slits and cramped interior reinforce the idea of a machine built for surveillance rather than combat dominance. The only known specimen resides at the Kubinka Tank Museum in Russia, reportedly captured by Soviet forces in Manchuria during 1945. That discovery has fueled speculation that the vehicle may have been transferred to Japan for testing, adding another layer of uncertainty to its origins. Without production records or operational logs, even basic questions, how fast it could travel, what weapons it might have carried, or whether it ever saw real deployment, remain unanswered. Technically, the Kugelpanzer abandoned traditional armored doctrine, steering by varying wheel rotation to pivot with minimal mechanisms. This unusual layout likely struggled on rough terrain, and the absence of suspension limited mobility. Rather than a practical weapon, it survives as a symbol of wartime experimentation, a mysterious project that pushed unconventional engineering ideas while leaving historians with more questions than clear answers decades later.